This is the full mission simulation review for the Community Colleges of Colorado team, Orbital Debris Redirection and Thermal Reentry, DOTS, and provides a video update of the progress of our payload. We recognize that by this point, our payload should have been fully integrated and running in a flight condition. As a result of a difficult-to-diagnose power module issue, we have been forced to run our primary experiment simulation using a 5-volt external power supply as opposed to the 28-volt the rocket will supply. After several days of troubleshooting the system, we traced the problem back to the GE Hammerhead DC-to-DC converter we had selected for our primary PCB. This module converts the 28-volt supplied to 5 volts provided to our Arduino and Raspberry Pi boards. But an unforeseeable result from the charging apparatus high-torque motor is a voltage kickback that was signaling the converter to shut down to protect the circuit. This was causing our Arduino Pro Mini to shut down and the Raspberry Pis to reboot on our third debris launch repeatedly. Once the problem had been diagnosed, we were able to run an entire simulation with the primary powered by a 5-volt power supply. The following video features our full simulation with that small alteration. However, we currently have calls into multiple electrical engineers, and we are researching the best replacement for this converter. We are confident that we will procure this component within the next 3 days after the holiday weekend and be fully operational. We wanted to provide our integration video by today so you can assess our readiness and make recommendations. As always, we appreciate the tremendous support Colorado Space Grant has given us. The following is the sequence of events our payload will experience at Wallops. For this purpose, team member Ryan Weed constructed and coded the Wallops timer event and telemetry simulator. This was used to test our payload using interfaces we will see at Wallops. Initially, we load the Wallops timer event and telemetry simulator in the Arduino IDE. For our simulation, we shorten the timer events for ease of viewing. The timer events have been tested by multiple team members with stopwatches to verify accuracy. After we send the start signal from the simulator, we verify GSE signal by light on the simulator and secondary PSB. The GSE provides power to the Teensy 3.6, which starts writing temperature data every 0.25 seconds to a Samsung Evo Plus 32GB micro SD card from 5 RTD100 probes. We visually verify operation by the orange light on the Teensy, and we also verify temperature data points in the Arduino window and on the SD card post-simulation. After the start signal, we also see the redundant A and redundant B both power on by indicator lights on both the simulator and the primary PCB. This powers the Arduino Pro Mini, which simultaneously starts to query the Teensy for temperature data and boots both Raspberry Pi 0Ws, all of which can be verified visually with indicator lights seen here. At the rocket's forecasted apogee, TE1, or timer event 1, is activated, seen here. Multiple events occur at this point. First, power switches over from rocket to internal power, a 3.7-volt LiPo battery, for secondary only. Then the Arduino turns on internal LEDs and signal Pis that the first launch, or our control launch, is about to begin. The 2 Raspberry Pi camera modules take control images along the X and Z axes and then record video for 10 seconds. The Arduino activates each launch tube in sequence by sending a signal to one of the 4 Savox digital mini servos to launch debris with a 15 millisecond stepper delay to ensure a muzzle velocity of less than 1 inch per second. The Pi cameras stop recording video and the Arduino signals LEDs to turn off. The Pis then compare the debris images to the control image, compile matrix changes, and send coordinate data back to the Arduino, which then sends telemetry data back and video matrix data to the SD cards. After this, the test launch sequence begins, which requires a charge on the plate of the Earth Atmosphere Chamber, or EAC. Here, the Arduino sends a signal to turn on the high-torque 6-volt motor of the charging apparatus and moves a high-tech Mega 6-volt servo to engage the polycarbonate charging plate of the EAC with rabbit fur. It charges for 2.5 seconds before the servo moves the fur away from the plate and the motor stops spinning. Then the entire sequence of the control launch happens again 3 more times. During this time, temperature data will be continually read and recorded until splashdown. At this point, we pull the SD cards from both the Pis and the Teensy and verify data storage. This simulation lets us see if the systems are performing together and collecting data as expected, ultimately to ensure the payload will run for the entire flight. Currently, the only issue that must be resolved before the integration readiness review is the power module problem, but we are highly confident that we can resolve this issue within the next 5 days after the holiday weekend is over and we are able to order and receive a new component. Once this slight change is made, we will have a fully functional payload and be ready to integrate successfully in June.